All right, question about number 33 in the homework. How many people got number 33? A particular vinegar is found to contain 5.7% acetic acid by mass. What mass of this vinegar should be diluted with water to produce a 0.750 liter of a solution with pH 4.52? And so we want a 0.750 liter solution of vinegar or acetic acid, actually just acetic acid, with a pH 4.52. All right, so we're given the pH of this solution. The pH is going to equal the negative log of the total hydronium in solution. And so when we measure it, but not just the total, this is the total hydronium at equilibrium. Because when you stick the pH meter in there, everything should have equilibrated by then. And so if we have an acetic acid solution, then there are only two things in here, acetic acid and water. And so the hydronium ion contribution will be two of them. There's going to be hydronium from the acetic acid, acetic acid can be abbreviated AC, acetic acid, or HAC. Plus the hydronium from, what's the other source of hydronium? Water. This is going to dictate how we do this problem. One of the things is maybe we could ignore the hydronium from water. Is that justified? And if so, why? Yes, but why is it justified to ignore the hydronium from water? Well, all right. This is basically the way I see this. I see they're giving us one equilibrium concentration. They're giving us the equilibrium concentration of hydronium. But I want to know, is this the equilibrium concentration? Because I have acetic acid, so step one would be the bigger K. That is acetic acid plus water. Did I already talk about HAC earlier? Did we use that? And so acetic acid plus water, this is going to give us hydronium and acetate. Ka for this is 1.8 times 10 to the minus 5. We can look that up in the book. And so we go through and we figure out the ice table for this. And then we go on to step 2. Step 2, we're going to generate some kind of hydronium here at equilibrium. And this is going to be the hydronium that we get from acetic acid. And then we go on to step 2, which will be H2O liquid plus H2O liquid. This is going to give us hydronium and hydroxide. And so what we could do here is this hydronium that was produced in step 1 will go down here. And so this is initial. The change is we're going to add some more hydronium to this from water. We'll call this from H2O. This is from HAC, hydronium. And the hydronium from water we call X. Just like the change up here would be called X. We start off with 0 here. And so at equilibrium, we're going to have a total hydronium That's going to be the hydronium that we generated from step 1 plus the hydronium that we generated from step 2. If we can ignore step 2, then that saves us a little bit of work. So that brings it down to 1 ice table rather than 2 ice tables we have to deal with. Can we ignore the hydronium that's produced from water in this case? And yes, and if so, why? Typically it's a small change because kW is 10 to the minus 14, 1.0 times 10 to the minus 14 at 25 degrees C. But there's another reason, and that is we can't always ignore it. We can't always ignore the hydronium, and we're assuming stepwise works, but we can't always ignore it. But in this case, we can ignore it because look at the pH. The pH, this is the power of the hydronium ion concentration. So the power of the hydronium ion concentration is between 10 to the minus 4 molar and 10 to the minus 5 molar. And so if it's 10 to the minus 4 to 10 to the minus 5 molar hydronium, what's the most hydronium that we're going to generate from water? kW. What is the most hydronium we're going to generate from kW? It can't go above this. 10 to the minus 7. If this were 0 and 0, then I'd get 10 to the minus 7, 10 to the minus 7 molar. But since I already have a lot of hydronium present, I don't have to generate nearly as much. And so the actual amount of hydronium I'm going to generate from water is going to be less than 10 to the minus 7 molar. More like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar. And so if you look at 10 to the minus 8 molar, will 10 to the minus 8 molar have any impact on this? Yeah, it's because it's orders of magnitude smaller. And so what we're going to do is we're going to say that the additional hydronium that we generate from step 2 is negligible. And therefore, that this pH is at the end of step 1. That is, we're just going to say that this is small. So small we can call it negligible. And therefore, we'll get the negative log of the hydronium. And the hydronium is going to be produced from step 1, the acetic acid step. And so we could figure out how much hydronium we generate from the acetic acid step. The amount of hydronium generated from the HAC step will be the anti-log. So we just take the 10 to the negative pH molar. And so this is going to be 10 to the negative 4.52 molar. And if we punch out that number, what does it come out to? 3.0 times 10 to the negative 5. Okay, we need one more digit because we're allowed 2 sig figs. 3.02 times 10 to the negative 5 molar. Okay, so this is going to be the HAC contribution of hydronium at equilibrium, because pH is going to be measured in an equilibrium solution. And so what that tells us is that we have, we're given one piece of data, although it took some work to figure it out, but we're given one piece of data in the ice table, and that is the hydronium ion concentration at equilibrium, which is going to be this, 3.02 times 10 to the minus 5 molar. All right, in an ice table, what are the values? Were we given the initial acetic acid concentration? No, we weren't. And so what we're going to call this is HAC initial. And what's the initial hydronium? That's going to be 0, and acetate, 0. And so we're just going to have water is nothing here. We're going to have minus X molar, plus X molar, plus X molar. And so right here we see what X has got to be. X has got to be 3.02 times 10 to the minus 5. And so the acetate concentration is 3.02 times 10 to the minus 5 molar. And the HAC initial is going to be HAC initial minus 3.02 times 10 to the minus 5 molar. I'll just leave off the unit there. leave out the units in the Ka equation. And so the Ka equation, we have the hydronium ion concentration at equilibrium times the acetate concentration at equilibrium divided by the HAC concentration at equilibrium. And so this is just going to be 3.02 times 10 to the minus 5 squared divided by the HAC concentration initial minus 3.02 times 10 to the minus 5. And so we only have one unknown here. We solve for the HAC concentration initial. Can somebody solve for the HAC? Times 10 to the negative. All right, so we'll have this is equal to 8.21 times 10 to the negative 5 minus 3.02 times 10 to the negative 5. And that's going to give us 5.19 times 10 to the negative 5. So let's just double check these concentrations by plugging them back into K and see if it works out or not. Did it work out? Okay, so this is good. Check is okay. And so what this means is this. This is the equilibrium concentration of acetic acid, but we don't make it. You know, when you make an acetic acid solution, you want a pH of 4.52. You don't mix up this much acetic acid, this much hydronium, and this much acetate separately. What you do is you mix up this 8.21 times 10 to the minus 5 molar acetic acid here. And so that means this 3/4 of a liter should be initially at a concentration of 8.21 times 10 to the minus 5 molar HAC. And then what happens is the acetic acid molecules will partially hydrolyze to form some hydronium and acetate, and we'll lose a little bit of the acetic acid, and we'll generate a pH, the desired pH, whatever that is. Okay, so this is a typical problem. But sometimes they take a typical problem like this and make it a little bit more complicated. And so what they want us to do is, well, how are we going to get this molarity here? What we're going to do is we're going to take a vinegar solution and then dilute it with water. And so they're asking how much vinegar is required to do this. So let's see. What mass of vinegar should be diluted? It's 5.7% vinegar. And so what we want to do is we want to figure out, how many grams of 5.7% vinegar is required to make that solution. And so this, we're just going to use some Chem 1A dimensional analysis. We have 0.750 liters of HAC solution. And this HAC solution has this molarity, and so it's going to be 8.21 times 10 to the minus 5 moles of HAC per liter of HAC solution. And so the liters of HAC solution cancel, and that gives us moles of acetic acid. Then we have 5.7%. So this is moles of pure acetic acid. And so we need to go from moles of pure acetic acid to what? To grams of pure acetic acid. And so we'll need the molar mass. Actually, should I just set this up? You want me to complete the calculation or just set it up? Should I complete it? All right, so that means I have to calculate the molar mass of acetic acid. And so we'll use this formula here. So I have 4 hydrogens. That's 4 times 1.01. 2 carbons, that's 2 times 12.01. I have 2 oxygens. It's 2 times 16.00. And so this is going to give us 4.04, 24.02, and 32.00. So it's 6, 0, 8, 10, 60.06. So I have 60.06 grams of pure acetic acid per mole of pure acetic acid. So moles of pure acetic acid cancel, leaving us with grams of pure acetic acid. And then I have this one, vinegar. This particular vinegar is 5.7% by mass acetic acid. And so what that means is this: for every 100 grams of vinegar, I have 5.7 grams of pure acetic acid. And so the grams of pure acetic acid cancel, leaving us with grams of vinegar, and that's what they want. How many grams of this vinegar do we have to dilute to make this solution? And so this is a Chem 1B plus a Chem 1A sort of dimensional analysis type problem. So what does it come out to? 0.064. 64 milligrams? Is that right?
Yeah.
I mean, 0.064 grams would be 64 milligrams. Yeah. 0.0640?
0.0648.
0.0648. Well, the molarity is kind of low. That must be, that vinegar must be very high molarity if we use just so little. Is that what other people got?
Yeah.
All right, then I guess that's it.
something like this in the exam, or like when you give us the pH and then you make us find the molarity of or concentration of hydrogen?
Yeah, could be. Could be. It's just the ice table. Ice table. You try to fill up the ice table as much as possible, and then look for the unknown. And so, yeah, it's possible. It's possible, but in the past I've kicked it up a notch. I've made step 2 required, so you had to work backwards. The pH I gave you is the pH at the end of step 2. Can you work backwards from step 2? Could you have worked backwards from step 2 here? Yeah, actually, it's not that hard. It's just, you'll have 2 unknowns. You have 2 unknowns, you'll have 2 equations. And then you just solve that system of equations. But it won't be as hard as the two unknown, 2 equation ones that you saw with simultaneous. Okay. It'll be a lot easier mathematically. And so I've done, I thought sulfuric acid was in your homework, but I thought there's another one of these with 2 steps. Sulfuric acid. Is there?
Something that's like.
I'm pretty sure sulfuric acid is in your homework. You're going to have one with 2 steps, where you have to do Ka1, Ka2, and then ignore Kw. And the pH is given. The pH is given, and you work backwards. You see something like that? Sometimes I do that one as an example problem. But,
It's 49.
49? Not exactly, but those are dichroic there acids.
Would it be like 46?
Number 46, 2 types of problems you have on the ice table when you start looking at the homework. One problem is you start from the initial and go to the equilibrium. That's one type. The other type of problem is like this one, where you start from equilibrium and then work backwards to initial. But it shouldn't matter which way you go. You just look for, there's usually just one unknown, you solve for that. If you're to make up the solution, you'd make it up as 8.21 times 10 minus 5 molar. Well, that's the initial concentration. That's how we stated. Like, for example, if you have 0.100 molar phosphoric acid, some of that phosphoric acid is going to hydrolyze. In fact, a pretty good percent. We saw about 36% hydrolysis, but we still call it 0.100 molar phosphoric acid. We don't call it 0.6 something molar phosphoric acid and 0.3 molar this and 0.2 molar that. We just take the initial and say, okay, whatever it does is going to hydrolyze, and then you figure out what happens. And so the other type of problem is like this, where let's see, it might be in advance. well, it's. Did I sign 88? No. All right. Actually, I can't find it right now. I think it's somewhere in there, or maybe I'm just forgetting. 88 is similar to what we just did, you know, except you have to do it preparing ammonia, HCl, whatever. Which of these solutes would you use? Actually, this one you have to figure out which of the solutes you use. But the type of question I just mentioned, where it would be two-step, is something like this, where you have H2SO4, and let's say we wanted a pH of 4.12 here. And so, you know, what must the H2SO4 molarity be? Well, I need to mix up the solution of H2SO4. I want a pH of 4.12. What should it be? You know? And so this is the same type of analysis that we do, because the pH is equal to the negative log of the total hydronium ion concentration at equilibrium. And so we've been talking about this over and over again. The negative log, well, what are the hydronium ion contributors to an H2SO4 solution? Well, H2SO4, we're going to have the hydronium from step 1, which is called Ka1. That's for H2SO4. We're going to have the hydronium ion from step 2, which we call Ka2, plus the hydronium ion from Kw. And so we got 3 hydronium ion contributing steps here. It would be nice if we don't have to deal with step 2 and step 3. That would be very nice, because then we only have to deal with one ice table. We say all the hydronium is generated in step 1. But in this particular case, can we ignore step 2? No, we can't ignore it. Why? Why can't we ignore step 2? No, some diprotic acids we can ignore step 2. For example, carbonic acid, we can ignore step 2. A bunch of other acids we can ignore step 2. This is special because no, it is H2SO4 is a strong acid, but step 2 is not the strong acid. Let me tell you what step 2 is. Ka1 is H2SO4. Ka2 is the Ka for HSO4 minus. What do you know about the Ka for HSO4 minus? Huh? No. The Ka for HSO4 minus is, well, I'll tell you what it is. It's what's the Ka for H2SO4? Yeah, very large. The Ka for HSO4 minus is 0.011, which tells you what? It's significant. And so in this case, it's significant, so we have to figure it out. Actually, this is an exam problem I gave. I don't remember when, but this is one of the exam problems I gave a while back. And so, yeah, is it possible? Sure. I've given it before. You know, 2-step. You have to work backwards. Would you worry about Kw? No, not at this pH. I'm not going to worry about Kw. So this one we're going to say negligible, but step 2 we cannot say is negligible. For certain diprotic acids we could, like if this were carbonic, no problem. Say it. But because of the relatively large K, we can't. And so how would you do this? Well, you just set up 2 ice tables and you work backwards and you just fill it out as best as you can. So we have H2SO4 plus H2O liquid. This is a one-way reaction. It goes to hydronium plus HSO4 minus. So whatever we have here, I'm going to just call this the H2SO4. What should I call this? Initial. I don't know what it is, but that's what I'm trying to find out. What do I have to make this initially? 0, 0. And how much of this am I going to lose? All of it. And so I'm going to end up with 0 molar here. And the hydronium concentration is going to be the same as the H2SO4 initial, and the HSO4 minus concentration will be the same as the H2SO4 initial. And then I go on to step 2. Step 2 is the second proton, hydrolyzing water, to form some additional hydronium and sulfate in this case. And so the hydronium ion concentration, I'll drop down here. The hydronium ion concentration is the H2SO4 initial, and the HSO4 minus concentration I'll drop in over here, call that HSO4 minus initial. And so this is my initial. The sulfate's going to be 0. How much of this am I going to lose? I don't know how much, because it doesn't go to completion, so we're just going to call it minus X plus X plus X. And so in equilibrium, I'm going to have HSO4 minus initial minus X. We're going to have the H2SO4 initial plus X, and then X. We got 2 unknowns. We've got 2 unknowns. We'll need 2 equations to solve it. What would the 2 equations be? I'll tell you one equation will just be the K. You know, Ka2 is equal to 0.011, which is equal to the hydronium ion concentration at equilibrium for step 2 times the sulfate concentration at equilibrium divided by the HSO4 minus concentration. And so this is just going to equal the HSO4 minus initial plus X times X divided by HSO4 minus initial minus X. All right, there's one equation. Give me another equation that we could use. We're going to ignore KW. Yeah, if you look at this, the hydronium from Ka1 is equal to HSO4 minus initial. The hydronium from Ka2 is equal to X. And so here we have a second equation we can use, then do some substitution and solve for one variable and substitute. And so this is just using the ice table as we have done, except it's not the same type of calculation each time. You know, you have to be flexible in the way that we can have other variables other than X that we solve for. So I'll let you finish this one if you want. All right, any other questions before we move on? 89?
Did anybody look up the solution in the solutions manual? The solution in the solutions manual is wrong. Actually, try this one. Let's do B here. Try B. Let me grab this. Maybe they fixed it. The previous edition, they had it wrong. Oh, they finally fixed it. Okay. Let me take that back. Yeah. Okay. Well, what's the deal with 89? We did something very similar to 89.
Solution manual, they assume that the initial hydrogen concentration is from the water, and they just solve. But you said that we do like the water as step 2, and then step 2 over to step 1.
Oh no. Okay. The way I do. Why did they assume that the initial hydronium is from water? There are two ways you could do this. How much hydronium did they get? Did they get a number, or did they just put the
Yeah, from water, like
1.0 times 10 to the minus 7? All right. Which one did you do, HCN or the, obviously HCN if you're doing hydronium. So let's look at HCN then. All right, we're looking at 1.0 times 10 to the minus 5 molar HCN. And you're saying that they put in the initial hydronium. Okay, so basically we have two equilibria going on here. We have Ka and Kw. Ka is like 10 to the minus, what's the Ka value?
6.2 times 10 to the negative 10.
And Kw is 1.0 times 10 to the negative 14. And so the way I would do this, I would start off with Ka and then go to Kw. But you're saying the book started with Kw and went to Ka.
No, they said with the hydrocyanic hydrolysis, and they for the hydroniums wasn't initially 0 molar, but they just put the hydronium from the equilibrium of water.
Yeah. They skipped this step, basically. Basically, they did this. They went step 1. I'm going to do it the whole way because I do it the same way each time. But they started with step 1 as H2O liquid plus H2O liquid. This is going to produce hydronium and hydroxide. And so initially, there's nothing, right? And then the change, and then at equilibrium. Well, we already know this one. 1.0 times 10 to the minus 14, 1.0 times 10 to the minus 14. Molar. This is Kw. Okay, then they go to step 2. When they go to step 2, they look at HCN will hydrolyze water, H2O liquid, to produce hydronium and cyanide. Here. And now we're going to drop down the hydronium that was produced in step 1 here. And so the initial conditions will be 1.0 times 10 to the minus 14 and 0. Is that what they got? See, what they did was they went ahead and did step 1 first as Kw and then went on to step 2, which is HCN. I would have done it the opposite way.
The opposite way, we did it in class, but with negative, the initial concentration was 10, something 10.
Well, yeah, but how did they solve this now? What did they do? They did the change, which is going to be plus x. Is that correct?
And also you missed the concentration of HCN initial.
Oh, oops.
Yeah.
Okay. HCN initial was 1.0 times 10 to the minus 5 molar minus x.
They just solved for
And so we're going to get 1.0 times 10 to the minus 5 minus x, 1.0 times 10 to the minus 14 plus x, and x.
wait, this is 1 times 10 to the negative 7.
Oops. You're right. That's wrong. Times 10 to the negative 7. 1 times 10 to the negative 7 plus x. Is that right? All right, so we just go to the Ka expression. The Ka expression is going to be the hydronium ion concentration times the cyanide concentration divided by the HCN concentration here. And so we'll have 1.0 times 10 to the minus 7 plus x times x divided by 1.0 times 10 to the minus 5 minus x. Yeah, then we do the simplifying assumption. Hope it works. And so we get 1.0 times 10 to the minus 7 times x divided by 1.0 times 10 to the minus 5. And that means x is, well, this is going to be 10 to the minus 2, and then divide both sides by 10 to the minus 2, so it's going to come out to 6.2 times 10 to the minus 8. Is that what you get for x? 6. They use the quadratic formula?
Yeah, they get,
Well, let's stop here and see if this is okay. Is this okay? We have to justify it. And so the percent change would be the change over the smallest. And so the percent change would be the change 6.2 times 10 to the minus 8. Now we have 2. We could compare it to 10 to the minus 7 or 10 to the minus 5. We're going to compare it to 10 to the minus 7 because that's going to result in a bigger percent change. And so this will be 1.0 times 10 to the minus 7, which gives us times 100%, which gives us 62%. It's too huge. And so the simplifying assumption fails, therefore we have to use a quadratic equation, which the book did. And what did they get for the x after using quadratic? Okay, so using the quadratic, we got x is equal to 1.24 times 10 to the negative 7. 1.44 times 10 to the negative 7. Okay. All right, then we go back here and let's go ahead and do the calculation. So we're going to make this 10 to the minus 7. So I'm going to change this to 10 to the minus 7. So I need to move it 2 over. So this is going to be 100 times 10 to the minus 7 minus 1.44 times 10 to the minus 7, which is going to give me 98.56 times 10 to the negative 7 molar. And then over here, I'm going to add to it. So I got 1.0 times 10 to the negative 7 plus 1.44 times 10 to the negative 7, which is going to give me 2.44 times 10 to the negative 7 molar. And then over here I get 1.44 times 10 to the negative 7 molar. Is that right? All right. Now we need to check our K value. So let's go ahead and check the K value. What does it come out to? It's okay? Checks out? Is this what the book got as their answer?
And then they calculate the pH.
And then they calculated the pH? Okay. What did they get as the pH?
6.6.
6.61? Based on the hydronium after step 2? Okay. And then they were done? That's the solutions guide. You have the old solutions guide, I think. Maybe. What do you have the white one like this? Oh. I'm sorry?
The old one was wrong.
The old one's wrong. Unfortunately, this one's wrong too. This is wrong. What's wrong? The solutions guide is wrong. This is totally wrong because what makes this totally wrong? The reverse of what? It doesn't matter. I mean, I guess we could have done we could have done it the other way. The book often does this, though. The book often will assume that water's at equilibrium, which is fine. We did it too. We did it this way a long time ago. I called it the Le Chatelier method versus the reset method. Your book is doing it the Le Chatelier method rather than the reset method, which is fine. I just prefer the reset method. I call it the Le Chatelier method because what's going to happen here? There's a major problem with how the book solved this. Do you see the major? This is why I didn't even announce it, because I would assume that you would notice it right off. This is impossible. This answer is impossible.
Step 1 third.
Yeah. You know, okay. How can we have two different hydronium ion concentrations in the same beaker? Is that possible? It's impossible. And so there's only one hydronium ion concentration, and what is it? It's this one. Well, if this is the hydronium ion concentration, then we just doubled the hydronium, which means Le Chatelier's principle says to shift this step 1 back to the left. Well, that means if this shifts back to the left because this hydronium is too high, this hydronium is going to decrease. Well, if this hydronium decreases, is this still going to check? No. And so what do we run into? We run into a stepwise failure. Stepwise fails. You cannot solve this
using stepwise like the book did because they forgot to check if step 2 perturbs step 1, which it does. And I could have started with HCN. If I started with HCN as my step 1, which I normally would have, because I don't like doing this here because the hydronium is going to change anyway, so why not just reset it to 0 and 0? And so I always do KW last. To do KW first is not the way you want to do it. Think about the last problem we did with acetic acid and vinegar. Would you have started that with KW first? You would have been wasting a lot of time. And so this is why I'm doing it the same way each time, no matter what the book does and how they solve it, because they often skip steps or they'll flip things around. Sometimes it's faster, and I think that's why they do it, but you can't always do it that way. Well, unfortunately, they made a mistake here because this for sure is going to result in a Le Chatelier shift left, which changes the concentration, which screws up this. So we could go back and fix step 1, but that's going to screw up step 2. We go back and fix step 2, and we're in this perpetual, endless loop. We can never get out of because we're trying to solve this stepwise. We can't solve it stepwise. We have to solve it simultaneous. All right. And so this is why I did HCN in class, because the book is wrong. The book's answer is wrong. This is a problem. You say, well, okay, why are you using this book then? There's these errors. Well, every single textbook out there, including TRO, which is the most popular book out there, has tons of errors. And so you have to just watch out for them. All right, so how do we solve it simultaneous? Go back in your notes and you'll see what we did. Okay. And so this is simultaneous for sure. Now, if the concentration were higher, if the HCN concentration, let's say the HCN concentration was 1 molar, this is why some people say, well, if it's stepwise, why don't you just give me a simple way to determine? No, there's no simple way because you don't know where the cutoff is. Because once we get a high enough concentration of HCN, then stepwise will start to work. How do you know? You just do it. You got to do it, each one. You can't say, okay, for HCN, it's going to be below this molarity and above this molarity. Do you want to memorize that for every single acid? Oh, it'd be horrendous. And so what you do is you just try it stepwise. If it works, great. If it fails, it fails. But don't assume if it fails in this case, it fails in all cases. Because it depends. There's multi-variables that go into this, and it depends on the concentrations, the K values, etc. And that's going to tell you what that cutoff is where stepwise is going to fail. But here, stepwise failed. I think if I went to maybe 10 to the minus 4 molar or 10 to the minus 3 molar, stepwise would succeed. That's a guess, but I don't know. I'm just going to try it and see if it works or if it doesn't. Okay. All right. Any other questions? Well, today I wanted to do a little catch up, and then we'll have lab. The lab today is short; doesn't take very long, and so we'll take a break right now, and then let me catch up a little bit in chapter 17, and then we'll start the lab.